welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 10, Lesson number 6 on bivariate data analysis. Ooh, that's a mouthful. Before we begin, let me remind you that you can find a worksheet and a homework assignment that go along with this video by clicking on its description or by visiting our website at www.emathinstruction.com. Also, don't forget about the QR codes. At the top of each one of our worksheets, you can scan this code with either your smartphone or with a tablet, and it'll bring you right to a video that's associated with that lesson. All right, let's begin. Bivariate data. Bivariate really means two variables, all right? And very often in the real world, what we want to do is think about an association that might occur between two variables. Ideally, so that we could use one variable to predict what's going to happen with the other one. Now let's take a look at exercise 1. Here's a really good example. A survey was taken of 10 low and high temperatures in Fahrenheit in the month of April to try to establish a relationship between the day's low temperature and high temperatures. All right, so just to make sure you get it, right, the idea would be on a day when the low temperature was 26, the high temperature ended up being 49. On a day when the low temperature was 28, the high temperature was 50. All right, not rocket science there, I understand, but that's it. Now, one thing that you're often asked to do is to create scatter plots. All right, this is as easy as plotting points. So in other words, that 2649 is thought of as the point 26, 49 and 28, 50. All right, so let's do that. Now, very often when these kind of scatter plots are made, the symbol that's used isn't a circle, but it's a square. But you can use a circle if you'd like. So 26, let's see, these go by 2, so 26 would be here. The vertical scale also goes by 2, so 49 would actually be right here. And very often they'll use like a symbol kind of like that. That's supposed to be a square. I know it doesn't look like it. Let's see, 28 would be here, and 50 would be right here. All right. 30 and 57, well, there's 58, so that would be 57. Just watch yourself, okay? Then we've got 32 and 54. Let's see, here's 50, 2, 4. Remember, it's all going by 2s here. All right, what did I get up to? 32, 54. Let's do 34 and 60. That's an easy one. 60 is one of those major grid lines. All right. Then we've got 35 and 58. So that's going to be right here. Should have actually been more down on that line, but that's okay. Let's see, 37 is right here, and 64 would be right here. All right. 38 and 66 would be up here. 41 and 63 would be something like right here, right in the middle of that box. And 45 and 72, that'd be a nice day in April, wouldn't it? A 45, 72 degree day. Of course, if you're watching this video and you're out in California, you're like, that's a terrible day. In upstate New York, it's awesome. So we definitely see a pattern, right? Generally speaking, as the low temperature goes up, the high temperature goes up. It's not a perfect pattern, but it's not a bad pattern. Now, letter B says, draw a line of best fit through this data set. Now, this is where it's actually very difficult for me to give you great instruction in a screencast. Because what a teacher would tell you to do, and I'm a teacher, is to take out your ruler, put it along that data so that it has about the same slope, try to have about as many points above the line as you do below the line, and then draw your line. I'm going to draw mine in red. And let's see, it's something like that. So I think I'm going to start it right about here and draw it like about that. That's pretty good. That's not bad because I've got 1, 2, 3, 4 data points above the line. Sorry, 5 data points above the line. 1, 2, 3, 4 below the line. I've got 1 right on the line. It's pretty good. That's not a bad line of best fit. The idea is that we want to use that line now to actually come up with answers, right? To predict things. Now letter C says, calculate the slope of this line by picking off 2 points, not necessarily data points. Okay? Now let me pick 2 points off of this line. Maybe go to a different color. Now how do I pick 2 points? Well, you basically pick any 2 points that you can easily read. Here's 1 point that I can easily read off the line, and that's at 32, what's over here? 246, 56. Okay, and another point I could get would be, I'm trying to use the ones I originally did. Let me pick this point. Maybe it doesn't go exactly through there, but close enough. 40, 66. All right. So, now calculating slope is something that we've done quite a bit. That's the change in y divided by the change in x, right? So that'll be 66 minus 56 divided by 40 minus 32. That's going to be 10 divided by 8. And I actually want this in a decimal. Forget about fractional slopes. I like it as 1.25. Okay? 1.25. That's it. So, we filled up the screen. We're going to keep working with this problem, but I'll make sure that graph comes with us to the next page. So, pause the video now and write down anything you need to. Great. I'm going to clear out the text. You ready? Here it goes. Let's take a look at the next screen. All right, there's that line of best fit, right? And there are those 2 points that I used. Maybe that's a little bit of a better line. Letter D says, use your line of best fit to estimate the high temperature for a day in April, given the low temperature was 42 degrees. Illustrate your answer on the graph. Now, I've already kind of done this in a certain sense, but the idea is we would come over here. Let me change back. I don't like the green so much. We'd come over here to 42. And then from 42, actually, let me go blue here. From 42, we would go up to the line, right? And then we'd go over. And granted, it's maybe not perfect, but it basically looks like it would come out to be 68, right? And that's what lines of best fit are useful for, right? We're trying to come up with this correlation, right, between low temperature and high temperature. How do they relate to each other? So we plot our data, we draw our line of best fit on, either way, and then we use it to help us predict what may happen in the future. So I wake up, it's 42 degrees outside, and now I know in all likelihood the high temperature is going to be 68. Will it always be 68? No, because this isn't a perfect correlation. And we'll talk about what makes things more or less perfect in terms of correlation as we go on in these statistical lessons. All right, but take a look at letter E. Would you characterize the relationship between the low temperature and the high temperature as a positive correlation, or a negative correlation? Explain. Pause the video now and write down what you think. Even if you don't have a good explanation, write down where you think it would be a positive or a negative correlation. All right, here it goes. Now, by the way, positive and negative aren't about it being a good correlation or a bad correlation, all right? In fact, I would call this a positive correlation because as the low temperature, do a little abbreviating, increases, the high temperature increases. All right, so variables can either be positively correlated, which basically means they move in the same direction. As one of them gets larger, the other one gets larger. Or there can be a negative correlation, meaning as one variable gets larger, the other one gets smaller. This might be, let's say you were recording how many minutes you spent in the gym versus your weight loss. Generally speaking, the greater amount of time that you spend, the greater your weight loss. So how about this? The amount of time in the gym versus your weight, right? So as the amount of time in the gym goes up, your weight goes down. Well, anyway, hopefully we'll see some better negative correlations than the one that I just came up with. But that's the deal with positive and negative correlations. Do the variables move together, or do they move in opposite directions? Okay, so I'm going to clear this out, copy down anything you need. Here we go. Great, let's keep going. Correlation versus causation. This is one of the most classic topics in all of statistics. Okay? Sometimes there can be a great correlation between two variables, but no causal relationship. In other words, you could easily have two variables that seem to move together. As one gets larger, the other one gets larger. As one gets smaller, the other gets smaller. Or it could even be a negative correlation and a really good one. Oh, as this is getting larger, this particular thing is getting smaller. All right? And a lot of times what will happen is people will draw causal relationships. In other words, well, I don't want that thing to get larger, so I have to stop that thing from getting larger, right? But as statisticians will say, correlation is not causation, okay? Causation, or a causal relationship, is literally when one variable getting larger causes the other variable to either get larger or smaller, all right? That's causal. So this is an important thing to understand about statistics, something that you'll definitely be tested on a Common Core exam. So let's take a look at some examples to clarify it, okay? Exercise 2. In each of the following scenarios, two variables are given that, if plotted, would have a strong correlation. In other words, a scatter plot where the data falls nearly in a line. Determine if there exists a causal relationship between the two variables. If so, which variable causes the other? All right, take a look at letter A. The high temperature in New York City and the number of bottles of water sold. So if I graph that, if I graph the high temperature, and then if somehow I could find data that told me how many bottles of water were sold, that would be a very strong correlation. Is it causal? And the answer is yes. It is causal with the temperature causing the water use. You might say that the temperature is the causal agent, right? It's not that we're drinking water and therefore the temperature goes up. It's that the temperature goes up and therefore we drink more water, right? Letter B. A person's height and a person's shoe size. That is very well correlated. Generally speaking, the larger that a person's shoe size is, the larger their height is. And the smaller a person's shoe size is, the smaller the person's height is. What do you think? Is that causal? No. Neither causes the other. In other words, right, just because you have a bigger shoe size, it doesn't cause you to be taller. If that was the case, then when I was in like 8th grade and desperately wanted to make the 8th grade basketball team, I would have just gone out and bought larger shoes to make myself taller, right? They don't cause one another, but they are highly correlated. Here we go. Letter C, a person's weight loss and the number of hours a person spends in the gym per week, right? That was the thing that I was botching on the other one. Is that causal? Think about it. And the answer is yes, it is. And we'll say this time, the hours spent cause the weight loss. In other words, it's not that you lose weight and that causes you to spend time in the gym, although an argument could be made that the more weight you lose, psychologically, that makes you more motivated to go into the gym, etc. So, I don't know, maybe that's not as cut and dry. I think if you give a good explanation either way, it would be fine, right? And letter D, The years of education a person achieves and the salary that person starts at upon entering the workforce. This is a huge correlation. This is why teachers oftentimes tell you, you got to graduate from high school, you got to graduate from high school, you got to go to college, you got to go to college, etc., etc. You know, my parents always encouraged me, don't just stop at college, go on, get a master's degree, get a doctorate, a PhD, get a law degree, whatever. And again, this is yes. All right, it is causal. And specifically, the years of education cause, boy, that is just non-acceptable handwriting. The years of education cause a higher salary. Now, I've been a teacher for a long time, and I know how teenagers like to argue. I know how 9-year-olds like to argue, and even my 6-year-old daughter. The point is, you know, you can always find exceptions to the rule, right? Always, right? And that's not what statistics is about. Statistics isn't about the outliers. It's not about Bill Gates dropping out of high school and becoming the wealthiest person in the world, right? That's not the deal, okay? Statistics is about what is happening on the whole, right? What's happening on the whole? And so if you want to argue that no, a person who drops out of high school can make more money than a person with a PhD, I don't disagree with you. That can definitely happen. But generally speaking, the more years of education you have, the greater your starting salary. All right. So pause the video now, discuss, think, and write down. Okay, here it goes. All right, exercise 3. This is a classic when talking about correlation versus causation. The table below shows the number of firefighters required to fight a given fire versus the dollar damage done to the house by a fire. So in other words, like somebody was studying this and they found, oh, for a particular fire, 5 firefighters were needed and it caused $15,575 of damage, okay? For another fire, 12 firefighters were needed, and it caused $35,400 worth of damage. We got it? Letter A. Are the data positively or negatively correlated? How can you tell? Pause the video now. All right, well, fires aren't a positive thing, but that's not what this is about. This is a positive correlation. All right, and the reason you would say so is because as the number of firefighters goes up, the damage does as well. Right? That's clear, right? 2, 2932, 16, 52,900. Letter B. Does the number of firefighters cause the damage done to the house? If not, what hidden variable is causing both variables to change? So in other words, this is a classic causation versus correlation problem. What do you think? Does the number of firefighters cause the damage? No, of course not. That would just be silly. No, right? But, and I don't know why I want to pick on them, but you know, you could have like politicians oftentimes confuse correlation versus causation. You know, and I could see some very, very silly politicians saying, well, look, I mean, more firefighters, more damage. Therefore, let's just reduce the number of firefighters that go fight a fire, and therefore there'll be less damage. Well, that would just be crazy, right? You know, the hidden variable that's causing both of these variables to change is the severity or size of the fire, severity of the fire. If you said the size of the fire, that would be true as well. This thing's got a great name in statistics. This isn't something that you need to know, but it's what's called a lurking variable. That is one of my favorite math teams ever. Lurking. You know how you have like a younger brother that lurks? You know, that's literally it. There's the size of the fire is in the background. We don't necessarily see it, but the bigger the fire, then the greater number of firefighters and the greater damage done, right? Those two things, number of firefighters and damage, very closely related, and yet neither one of them causes the other. It's the size or the severity of the fire that does. All right? Doesn't feel like we're doing a lot of math here, does it? Feels like what we're doing is a lot of discussion. There's nothing wrong with that. And don't think it isn't math, because it is. All right, pause the video now if you need to, and then I'm clearing out the text and we're wrapping it up. All right, here we go. So today, we started talking for the first time about bivariate data analysis. Bi meaning two, variate meaning variables. We're going to spend a lot of time on this. We're going to use our calculators in the next lesson and see a lot of different things. But the big picture is what we're always trying to do is use one variable to try to predict what the other one will be doing, right? Sometimes one variable causes another one to do something. Sometimes it's only a correlation though, and there is no causative effect. For now, let me thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving.